wanted to look at an example of electric charge, and in particular, the electric charge that's stored in a crystal of sodium chloride. And we're going to calculate actually how much electrical charge of sodium, positive sodium ions is in the crystal, how much charge is owned by the negative chlorine ions inside the crystal. So I've got a pack of salt here, and just so we know the scale, here's a salt crystal. And of course you can't see it because that single salt crystal is so tiny. I'm going to be generous and I'm going to call its size 1 cubic millimeter. So 1 millimeter by 1 millimeter by 1 millimeter. That's 1 cubic millimeter. It's smaller than that, but it's approximately that size. It's roughly that size. And so we're going to calculate in that tiny speck of tiny grain of sodium chloride. We're going to calculate how much charge is owned by the sodium ions, how much charge is owned by the chlorine ions in the sodium chloride. So let me start by putting on the whiteboard, switching on the whiteboard. And so the question we pose to ourselves is how much charge is owned by the positive sodium ions in that little crystal? How much charge is owned by the negative chlorine ions in that crystal? So let me just write down. And let's go ahead and make the calculation. So the starting point is that the size of the crystal, I said generously, was 1 cubic millimeter. And so we know the volume of the crystal. It's 1 millimeter cubed. Let me write that in terms of centimeters cubed. That's going to be a bit more convenient for the units I'm going to use. And so that would be 10 to the minus 3 centimeters cubed. You know, there's 10 millimeters in a centimeter. There's 100 millimeters squared in a centimeter squared. There's 1,000 cubic millimeters in 1 cubic centimeter. Anyway, that's a starting point. The first thing I'm going to do, actually the first thing I already did, was look up the density of sodium chloride. The reason I looked up the density of sodium chloride because I really want to figure out the mass of this 1 cubic millimeter of sodium chloride, because that's going to help me figure out the number of ions, sodium ions, chlorine ions in this quantity, this grain of sodium chloride. So I did cheat and look up the density, rho I'm going to call it, of sodium chloride, and I found it to be 2.2 grams per cubic centimeter again. So armed with that piece of information, I can then calculate the mass of my little grain of sodium chloride. The mass of the grain of sodium chloride, I call that lowercase m, it's going to be in grams, is the density of the sodium chloride, that's the rho, times the volume of my grain of sodium chloride, that's the V. And so I've got 2.2 grams per centimeter cubed times 10 to the minus 3 centimeter cubed. I'll multiply those together. I'm going to have 2.2 times 10 to the minus 3 grams. That's the mass of the sodium chloride grain. Next step in my calculation, I want to figure out the number. I want to figure out the number of ions of sodium or ions of chlorine. Figure out the number of ions of sodium or chlorine I'm going to actually first figure out the number of moles of sodium chloride that I have in my 2.2 times 10 to the minus 3 grams of sodium chloride. And so for this calculation, and I looked up another number, but I kind of knew this number because I could work it out knowing a little bit about sodium and chlorine. I needed the molar mass of sodium chloride. Now, the molar mass is how many grams 1 mole of sodium chloride weighs. The mass of one mole of sodium chloride. And so I'll give that the symbol uppercase M for molar mass. And the molar mass is 58.5. And its units are grams per mole, because it's how many grams are in 1 mole of sodium chloride. As I say, I could have worked it out. The molar mass of sodium is 23 grams per mole. The molar mass of chlorine is a little over 35.5 grams per mole. And I could have just said that my sodium chloride is 1 part sodium, 1 part chlorine, just added together those 2 molar masses. But anyway, this is the molar mass. To then calculate the number of moles that I have, and I'm going to use the symbol lowercase m for the number of moles. This will be the number of moles of like sodium chloride molecules. It will also be the number of moles of individual sodiums, ions, and individual chlorine ions. So it's a number that represents all of those 3 things. All I've got to do is take the mass of my particular sample grain of sodium chloride, that's the lowercase m, divided by the molar mass, that's the mass of 1 mole of sodium chloride. And I've already done this calculation, so it's 2.2 times 10 to the minus 3 grams divided by 58.5 grams per mole. And this number came out to be 3.8 times 10 to the minus 5, and that's units is moles. Okay, so now I'm going to calculate the number of, would be sodium chloride molecules, or it would be the number of sodium ions or the number of chlorine ions in this number of moles of molecules or sodium or chlorine ions. So I'm going to give the number of ions the symbol uppercase N. It's going to be the number of moles times Avogadro's number. This is a number that you know better than I know. It's 6.02 times 10 to the 23 is the number of molecules or atoms or ions in a mole. And so I've just got to multiply my number of moles, which was 3.8 times 10 to the minus 5 moles, by the number, by Avogadro's number, 6.02 times 10 to the 23. I've already done that, and it is 2.3 times 10 to the 19. So that's a lot of molecules, or a lot of, in our case, we're interested in the ions, a lot of ions. Now we know how many ions we got. How much charge is owned by those positive sodium ions? How much charge is owned by those negative chlorine ions? Well, each ion has a charge whose magnitude is the electronic charge, 1.6 times 10 to the minus 19. And so all I got to do is multiply the number of sodium ions by 1.6 times 10 to the minus 19, and that will give me the amount of positive charge that's owned by all the sodium ions. And I could do the same thing for the chlorine ions. I could multiply the number of chlorine ions by minus 1.6 times 10 to the minus 19 coulombs. That would give me the charge owned by the the negative chlorine ions. Let's do the calculation for the sodium ions. I'm going to call their charge Q, and I'm just going to multiply the number of ions there are, that's the uppercase N, by the electronic charge, 1.6 times 10 to the minus 19. And if I multiply those two numbers, you think about it, I got 1.6 times 10 to the minus 19 times 2.3 times 10 to the 19. So the 10 to the minus 19, 10 to the 19 cancel each other out. I really just got 1.6 times 2.3, and 1.6 times 2.3 comes out to be 3.6. And that's 3.6 coulombs of charge. And so that's the coulombs of charge, positive 3.6 coulombs that are owned by the sodium ions. The chlorine ions, well, they own minus 3.6 coulombs of charge in our little grain of salt. Now, that's an interesting result. When you charge an object by rubbing cat's fur on a plastic rod, or rubbing silk on a glass rod, you will typically build up charges that are nanocoulombs, microcoulombs of charge. A coulomb is actually a huge amount of charge. It's just huge quantity of charge. We're not exposed through friction or rubbing to coulombs of charge. We're exposed through friction and rubbing to micro and nanocoulombs of charge. So there's a massive, even in that salt grain was tiny, right? You couldn't see that salt grain. It was so tiny. But that tiny, tiny salt grain contains this huge, huge, huge quantity of charge. There would be enormous forces, incredible forces, if I held in my hands positive 3.6 coulombs of charge in one hand, negative 3.6 coulombs of charge in the other hand. I'd be completely destroyed by trying to do that. So that amount of charge is huge. And if you'd had two isolated charges equal and opposite of those values, that would be enormous catastrophic forces between. And so it's incredible to imagine. It's amazing to imagine that even within a tiny grain of salt, a little grain of salt, there's this huge hidden volume of electrical charge that unleashes powerful electrical forces. Well, that was meant to be an example of working and thinking about electrical charges. As I say, we figured out the electrical charge of the ions in a salt crystal. We started with an estimate of the volume of the salt crystal. We figured out, therefore, the mass of the salt crystal, the number of moles in the salt crystal, and the number of ions in the salt crystal. And finally, knowing the electronic charge, we were able to calculate the charge that's owned by the positive sodium ions and the negative chlorine ions. And so that was our problem. What we discovered in the way is the huge, huge, huge amount of charge inside a grain of salt. So next time you put salt on your dinner, remember that.